Hello everyone, welcome back to our YouTube channel. The topic to be discussed is on electric field intensity due to an infinitely long straight charge wire. So first of all, let us consider an infinitely long charge wire like this. Say the charge is uniformly distributed. So now, to calculate the electric field due to this charge wire, let us draw a Gaussian surface in the form of a cylinder. Let the radius of this cylinder be r and the height of this cylinder be h. And lambda is the linear charge density. So now we divide this Gaussian surface into three regions. Say region 1, region 2 and region 3. So if ds is a small area element of this region 1, the direction of this is this, and here in region 3 the direction of the area, it is in this direction, and if we choose any small portion on the curved surface, say ds, and it is in this direction, it is along the radius of the cylinder, and the electric field, it is also in this direction. So this is E. So now let Q be the charge enclosed within the Gaussian surface. So therefore lambda is equal Q divided by H. This Q is the charge enclosed within the Gaussian surface. So the height of the Gaussian surface, it is H. So therefore lambda is equal Q by H. So this implies that the charge is equal lambda H. So now let us apply Gauss law. According to Gauss law, it states that the surface integral of electric field over a closed surface, it is equal to 1 by epsilon naught times the charge enclosed within the surface, and in this case the charge is Q. So this integration, it is equal to integration of region 1 E dot ds plus integration of region 2 E dot ds and integration of region 3 E dot ds, and this is equal 1 by epsilon naught times Q. So as we can see from here, in region 1 the electric field is in this direction, ds is in this direction. So the angle between this electric field E and ds, it is 90 degree. So similarly, in region 3, the electric field, it is in this direction, like this, but the direction of this area ds, it is in this direction. The angle is 90 degree. We have learned earlier that if you have two vector a dot b, then this is equivalent to mod of a, which is simply a, mod of b, which is simply b, and then cos theta. Now, if theta is equal to 90 degree, then this dot product a dot b is equal to 0. So similarly, as we can see from here, the integration of region 1, this one, it is equal to 0. The integration of region 3, this one, it is also equivalent to 0, because the angle between electric field and ds in region 1 and region 3, it is 90 degree. So now we are left with this integration of region 2, so E dot ds. So this is equal to 1 by epsilon naught times q. Also, as we can see, in this region 2, the electric field, it is in this direction, and the direction of this area, it is also in this direction. They are in the same direction. So if two vectors are in the same direction, the dot product between them, if you have here a dot b, if theta, it is equal to 0 degree, like in this case in region 2, ds is in this direction, E, it is also in this direction. So the angle between them, it is 0. So cos of 0 is 1. So a dot b, it is equal to ab. So therefore, this equation becomes E ds. So this one is equal 1 by epsilon naught times q. So this is integration of region 2. So since the charge is uniformly distributed, this electric field we can take out from this integration sign, and then we will remain with ds. This is 1 by epsilon naught times q, and this equation can be rewritten as E, and this integration of ds in region 2, it is nothing but the curved surface area of a cylinder. The curved surface area of cylinder is equal to 2 pi r h. So this is equal 1 by epsilon naught times. So here instead of q, I will substitute by lambda h. So this one, it is lambda h. This h and this h will go. So this E is equal to 1 by 2 pi epsilon naught. So lambda divided by r. So this is the magnitude of the electric field at any point which is at the distance r from this charge wire. So if you want to express this one in vector form, so we can write E equal 1 by 2 pi epsilon naught lambda divided by r cap. Here r cap is the unit vector which is along the radius. Or if you want to express further, this r cap multiply with magnitude of r, it is equal to vector r. So this r cap, it is equal to r vector divided by r. So how do you get this? If you have a vector, say a, like this a vector can be written as mod of a cap. So mod of a, it is simply a, so a cap, like this. A cap is a unit vector. So similarly, if you have r vector, we can write r cap. So if we substitute this value of r cap in this equation, this electric field is equal to 1 by 2 pi epsilon naught, then lambda. Then instead of r cap, I'll put with r vector. So this is vector divide. So 1r from this, and with this r, we will get r square. So this is the expression of the electric field due to this uniformly charged distribution. So now we will discuss these numerical problems. The question says, an infinitely long positive charge straight wire has a linear charge density lambda. The unit is coulomb per meter. An electron is revolving around the wire as its center with a constant velocity in a circular plane perpendicular to the wire. The question says, plot the graph of the square of velocity, that is v square, as a function of charge density. So we know that if we have an infinitely long positive charge wire, the electric field at any point which is at a distance r from this charge wire, say somewhere here, is E equal 1 by 2 pi epsilon naught lambda divided by r. Now the question says, an electron is revolving around the wire as its center with a constant velocity. So let us imagine that this is the electron. It is revolving like this in a circular path. Then this electron will experience an electrostatic force F equal EE. This is the magnitude. Since this electron is revolving, it provides the necessary centripetal force, and the centripetal force F is equal mv square divided by r. So if we equate these two forces, we can write F equal E equal mv square divided by r, or mv square divided by r, this is equal E. Instead of capital E, I will put 1 by 2 pi epsilon naught lambda divided by r. Suppose this r get cancelled. So here we can write mv square is equal to E divided by 2 pi epsilon naught lambda. From here we can see that v square is proportional to lambda. So therefore, if we plot the graph of v square as a function of charge density, the graph will look like this. this one is lambda, and this one is v square. It is a straight line like this. So now we will discuss the electric field intensity due to uniformly charged infinite plane sheet. So let us consider an infinite plane sheet. Say the charge is uniformly distributed. Let sigma be the surface charge density. Now we will draw a Gaussian surface in the form of a cylinder. We will divide the Gaussian surface into three regions. This is region 1, this is region 2, and this is region 3. The direction of the electric field, it is in this direction or in this direction. Here in region 1, the direction of the small surface area, it is in this direction, ds. Here in region 2, the direction of a small surface area, it is in this direction. And here in region 3, it is the curved surface area, and the direction of the area, it is in this direction. So now let Q be the charge enclosed within the Gaussian surface. So now we will use Gauss law, that is E dot ds over a closed surface. This one is equal 1 by epsilon naught times Q. Let capital A be the area of this, also the area of this. So what is sigma then? Sigma equal charge per unit area, and this Q is equal to sigma A. Remember that this Q is a charge enclosed within the Gaussian surface. Now this integration turn out to be integration of region 1 E dot ds plus integration of region 2 E dot ds plus integration of region 3 E dot ds, and this is equal 1 by epsilon naught times Q. So clearly from here, the angle between E and ds in region 1, it is 0 degree. Both E and ds, they are in the same direction. So therefore, the integration of region 1 is simply E ds. Similarly, the integration of region 2 is E ds. However, the integration of region 3 is 0. This is ds, this is E. So therefore, integration over region 3, it is 0. So E ds and E ds, this one we can add. So it becomes twice E ds. So you can put 1, which is equal to 1 by epsilon naught times q. So the charge is uniformly distributed. So E we can take out. The integration of this ds, it is A. As we have mentioned earlier, the area of cross section of this is A. So this is equal 1 by epsilon naught times q. But q is sigma A. So AA will get cancelled. So E is equal to 1 by epsilon naught sigma, or E equal sigma by 2 epsilon naught. So this is the magnitude of the electric field due to an infinite plane sheet. So now we will solve another numerical problems. The question says, two infinite parallel plane sheet have uniform charge densities plus minus sigma. What is the electric field in number A, the region between the plane and outside the plane? So there are two plane sheet. One is this, and another plane sheet is this. The charge is uniformly distributed. Say one plane, it is with plus q. Another plane sheet, it is with minus q. So first of all, let us assign electric field from left to right to be positive, and the electric field from right to left to be negative. So now we have three regions. One is this, it is outside the sheet. This is also outside the sheet, and this point, it is in between these two sheets. Let me mark this one as capital A, this one as capital B, and this one as capital C. So now, let E1 so now the electric field at A due to plus Q, since this one is, so now the electric field, so now the electric field at A due to this plus sigma, it is in this direction, because the electric field, it is always away from plus. So the electric field due to this plus sigma, it is sigma by 2 epsilon naught. So let me put as minus. Now, the electric field at A due to this minus sigma, it is in this direction. We have learned earlier that the electric field for negative charge, it is towards. So therefore, this is minus. So the electric field due to this minus sigma, it is in this direction toward that sheet. So the electric field due to this minus sigma, it is plus sigma divided by 2 epsilon naught. It is in this direction. As we have assigned, the electric field from right to left is negative. This one is negative. So from left to right, it is positive. Now, let us see the electric field at B due to this plus sigma. So the electric field at B due to this plus sigma, it will be in this direction. It is from left to right. For plus, it must be away, like this, at this point. So let me mark sigma divided by 2 epsilon naught. Now, what is the electric field at B due to this minus sigma? It will in this direction. Due to this minus sigma, we know that the electric field, it is towards the negative. So therefore, the electric field due to this minus sigma at this point B, it is also in this direction. So since it is from left to right, so this one also, it is sigma divided by 2 epsilon naught. Again, the electric field at C due to this plus sigma, it will be away from this sheet. So it is like this. Sigma 2 epsilon naught, it will be positive. And due to this minus sigma, as we have discussed, that it will be towards the negative. So this field will be in this direction. So as we have assigned, this one is minus sigma divided by 2 epsilon naught. So number A. So what is the field in the region between the planes? This sigma by 2 epsilon naught and sigma by 2 epsilon naught, they are in the same direction. So the net field at this point B, we have to add this and this. It becomes sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So here, we can take common sigma by 2 epsilon naught. So 1 plus 1. So this one become 1 plus 1 is 2 sigma by 2 epsilon naught. So 2 will get cancelled. So the electric field in between this plate, it is sigma by epsilon naught. And the second question is, we have to find the electric field in a region outside the plane, either EA or EC. So let us see what is EA. One, it is in this direction. The other, it is in this direction. They are equal in magnitude, but opposite in direction. So therefore, if we add these, we'll get 0. Similarly, here also, if we add these two, we will get 0. Here also, EC, it is 0. Sigma by 2 epsilon naught and sigma by 2 epsilon naught. So one, it is positive, one it is negative. So from here we conclude that in a region between, so in a region between the plane, E is equal sigma by epsilon naught, but outside the plane, in a region outside the plane, E is equal to 0.